So today we are here from Crowley to talk about vessel electrification and future fuels. So I'm Eileen Tausch. I'm a senior electrical engineer on the R&D team. My background is in naval architecture and marine engineering from the University of Michigan. In the past 8 years of my career, I've kind of transitioned over to the electrical side. So really putting that education to good use. And I also have Curt Leffers here with me.
Thanks a lot, Eileen. Good afternoon, everyone. It's a pleasure to be as part of your Sustainability and Ship Design Conference. My name is Curt Leffers. I lead the research and development team for Crowley Shipping. And my background is primarily in marine engineering with a mechanical engineering background and mostly in the world of engineering consulting. So it's a pleasure to be with you, and we look forward to presenting to you today.
So today we're going to start with a brief introduction of Crowley and sustainability goals, which is really allowing us to present at this conference. Do a discussion on electrification, and then Curt is going to take over to do a presentation on future fuels. So Crowley was founded in 1892. It's a privately held, U.S. owned and operated logistics, government, marine, and energy solutions company headquartered in Jacksonville. Services are provided worldwide we now have 5 primary business units. The slide is a bit outdated. We have Crowley Logistics, Solutions, Shipping, Fuels, and the new addition is Wind Services. The Crowley employs upwards of 6,000 people and has revenue over $2.5 billion. They are, I believe, the largest U.S. Jones Act operator of vessels. So Crowley's purpose and values, I think, are quite relevant this day and age, and really tie into what we're going to discuss today and what you've been discussing for the past day and a half. So purpose, bravely advancing what's possible to elevate people and planet, and values, integrity, sustainability, and drive. And so in today's current climate of the maritime industry, with the IMO goals and the focus on marine decarbonization that we're seeing, Crowley's made 2 ambitious commitments. By 2025, Crowley will be the most sustainable and innovative maritime and logistics solutions provider in the Americas. And by 2050, Crowley is committed to reach net zero emissions across all scopes using the science-based initiatives. So in an effort to realize these goals, Crowley has developed a research and development team. And the research and development team is focused on 6 key verticals, which I had in my previous notes that I've lost. So Curt's gonna list the verticals.
Oh, sure. Thanks a lot. So our key verticals in research and development are new concept vessel design, fleet efficiency improvement, microgrid solutions and electrification. We're also very focused on decarbonization research and future fuels evaluation. And part of our focus is also on commercialization and pursuing funding opportunities and third-party partnerships.
Thanks, Curt. I will blame that on still being new. So I think 2 recent investments that Crowley's made really focus and emphasize this endeavor. And the first is Zero Emissions Industries, which is a hydrogen technology provider in the maritime space. So the investment from Crowley was mainly to shorten our learning curve on hydrogen and figure out how and if we can use hydrogen within our fleet. And a Carbon Ridge investment, which is a startup in the carbon capture space, taking a carbon capture technology and marinizing it in containers. So today we see ourselves in a new era of another revolution in propulsion systems. There's a large focus on decarbonization. And looking back, we can see that there have been a few in the last couple hundred years going from wind to steam or coal to oil, using diesel and HFO, and now in decarbonization with a large focus on not using carbon-based fuels and finding alternative technologies. So with that in mind, it brings us to the topics we're going to discuss today: electrification and decarbonization and future fuels. So what is electrification? The process of replacing technologies that use fossil fuels with technologies that use electricity as a source of energy. And electrification isn't the final or the whole solution, and it doesn't necessarily mean a reduction in carbon emissions, depending on how you use the terminology. It allows greater flexibility in implementing the new technologies. So why do we need it? There's no clear answer to the future of marine propulsion. There's a lot of maybes and question marks out there right now, and a lot of ideas in how we can reach our goals. But a lot of the solutions include one common factor, and that's electrons. So electrification allows multiple sources of power to contribute. We have generators, batteries, fuel cells, solar, and it allows greater flexibility in expanding the system at later dates. So there's a lot of future proofing involved. What is the technology going to be in 15 years? We don't have that answer right now. So designing the system to accommodate as much as possible is key. I want to clarify one thing. Diesel electric systems have remained fairly common over the last 50 years. It's not a new thing. And that's just where alternators are added onto the diesel engines to create electricity from the mechanical energy. So rather than the engine turning the shaft directly, the electricity that's created gets passed through switchgear to electrical propulsion motors to turn the propeller shaft. And this has typically remained an AC alternating current system, and was often pretty complicated. So in discussing electrification moving forward, I'm going to focus more on the way we're discussing it now, which is a bit newer. The topic is more focused on hybridization, so using multiple sources of power, and decarbonization. So we'll talk a bit about, and stay pretty high level about some of the technologies that are enabling electrification and are the reason behind this transition. So first we have fuel cells, and Curt's going to talk a lot more about the fuels that go into fuel cells. So I'm going to focus more on the output of the fuel cells. So it converts chemical energy of hydrogen to electricity, and it results in direct current or DC power. And the output voltage varies with the load. So the higher load, the lower the voltage. Very quick overview. Next, we have batteries, and lithium-ion batteries are more where my expertise plays. So they're rechargeable energy storage systems using lithium ions as a key component of electrochemistry. And I'm sure we all have laptops and cell phones that all have lithium-ion batteries involved. So the marine systems they take lithium-ion cells and package them in a way to make the mechanical form factor more friendly for larger installations, and the systems are marinized for installation in ships. So the chemistries that are most popular are NMC, nickel, manganese, cobalt, LFP, lithium iron phosphate. And these are the two that are most common in automotive as well. And then lithium titanium oxide, which is a little bit different, but still relevant in the marine industry. So batteries produce DC power, and similar to fuel cells, the output voltage can vary, both with the battery state of charge and with how hard you're using the battery. So if you're drawing a lot of current and you're at a low state of charge, your battery is going to be at a pretty low voltage. Whereas if you're at a high state of charge and you're not using the battery very hard, you're going to stay at the top of the range. Next one. So both the fuel cells and the batteries produce DC power, which is key in another part of the transition in the industry, which is a shift from an AC propulsion system, as we've seen in the diesel electrics, most of the diesel electrics that have been in operation, to a DC propulsion system. So the generators and motors will remain AC. So these aren't changing too much. Obviously, there's always a drive for greater efficiency to see more fuel savings. There's also some new technologies in the DC grid market that's enabling this shift. DC-DC converters, DC-AC inverters, DC-DC rectifiers, DC circuit breakers. I'm not going to go into too much detail on these just because you can fill a whole hour just talking about these technologies. There's some interesting papers that have gone into more into the weeds with the benefits of DC technologies as compared to AC that I would be happy to share. But the reason that we're seeing this shift is it's more efficient with adding these new technologies. So if you have the batteries and the fuel cells producing DC power, it's easier to implement more of these technologies into a DC bus than it would be to convert the power from DC to AC back to DC. We can go next one. So for an example of what an AC bus would look like, this is just a typical diesel electric. You would have just a propulsion generator creating AC power, typically 480 volt, 690 volt, or at the higher end, sometimes there's 4160 VAC, and these are all at 60 hertz in the US. So it creates AC power to a bus, which is then distributed to the propulsion motor, commonly through a variable frequency drive, which is the current state of the art. We also see the hotel loads are fed from this, and that's the lights, the pumps, anything that is non-propulsion related, but electrical on a ship. And if you compare this to the DC system, we lose a lot of the circuit breakers. So instead of having these current interrupting devices, we have rectifiers, inverters, DC-DC converters, which are used, which have fuses inside, which will interrupt the current. And I did not put batteries or fuel cells on here, but those would be connected directly to the bus as well. There's different ways you can implement this technology. And I think what's key to really understand here is that there is a shift in the technology that is used on vessels. It's not new technology in the sense that it's novel, but it's new to the marine industry. And it looks different. There are a lot more cabinets and fewer moving parts. Oh, we're good. Okay. So when do you use new technologies? When do you use fuel cells? When do you use batteries? When do you use a combination of both? I think it's important to understand that not every technology fits with every application. There is a fine line between optimism and realism in designing a ship right now. And I think it's quite important to really understand how the technology is going to be used to ensure that there's actually a fuel reduction and you're not just, painting a green battery on the side of a boat for the press. So things to take into account: vessel size. Is the boat really large? Does it take a lot of power to push through the water? Is it really small? Is there enough physical space to put this new technology in the vessel? Vessel speed. I'm sure we've all seen speed versus power curve. The faster you go, the more power you need. The longer you go fast, the more energy you need. So the battery size or the fuel you need to store on board gets quite a bit larger. So that's related to the route length. Refueling and charging opportunities. Does the boat stop by the pier often enough to refuel? Curt will show a slide that shows the relative energy densities of the fuels. So some require significantly more volume on board and weight to carry the same amount of energy as our standard diesel right now. So you may need to refuel or charge more often. Does the boat have a consistent route? Is it a ferry that just goes back and forth on a consistent basis with a consistent schedule? Or is it a fishing boat, for example, which may go out for a weeks at a time? Is there fuel available where the vessel is? This can be a bit of a chicken or the egg scenario. And it's a discussion that we're having a lot with some of the future fuels that Curt will discuss. But for electrification, is shore power available? Is there enough shore power at the terminal to fully charge the vessel? So while a healthy dose of realism is important, Most applications can benefit from electrification and onboard energy storage. It just depends how you use them. So focusing more on the battery aspect right now, there are some different ways, different applications that you can use this technology. You can go full electric, so you operate only on batteries. You're not using a generator at all. So this we see more often in passenger vessels or ferries or the tugboat that I'll discuss in a few minutes. This is very route dependent to ensure that you can get enough energy storage on board. So your peak shaving. This is essentially where you run a generator or prime mover at a set point. So if the most efficient point of the generator is at 85%, then you run the generator at 85%, and the batteries are used to absorb anything below the set point, and it discharges anything above that set point. So you're eliminating the quick load changes of the generator. Have a boost function, which is similar to peak shaving, just at a longer time frame. So the battery will be discharging or charging for longer periods of time. Whereas with peak shaving, we often see it's happening at 100 times a second. Spinning reserve. Spinning reserve is more relevant on vessels of dynamic positioning, where there needs to be a secondary source of power online and readily available. So we see this a lot with the offshore vessels. So rather than having to bring an extra generator online, only for when the vessel's going is dynamic positioning, the batteries can serve as this extra source of power, which saves a lot of time operating a generator at idle. We often see batteries having a dual purpose as peak shaving and spinning reserve on these types of vessels. Load leveling is it's similar to all the other ones, and then ramp support we'll often see with these alternative fuels such as fuel cells. Fuel cells don't have as fast of a response rate as a diesel engine, so they'll be used in combination with batteries, and batteries can provide that instantaneous response to allow the fuel cells more time to ramp up and down. This provides the operators with a much more responsive vessel. Shore charging. So with electrification, I'm still focusing mainly on the battery operation. To maximize the carbon emissions reductions, shore charging is often used, and most of the time shore charging will be used for vessels with shorter routes that operate close to the terminal. So we'll see this a lot with, again, passenger vessels and tugboats. So we won't see, it will be much more rare to see shore charging, not cold ironing, not shore power, but actual charging of the energy storage on board of cruise ships or container ships with much longer routes. Right now, we're still in that smaller category. So there are some considerations to take into account with shore power to make sure you can maximize the carbon emissions reductions and fuel reduction. Charging requirements. How quickly does your boat need to charge? How high it powers? So we're seeing different ranges starting from less than a megawatt of charging power up to upwards of 14 megawatts in downtown Seattle. So the technology required to do the actual transfer of electricity, to do the actual charging, is quite different with both scenarios. The infrastructure required, is the power available? Is there a substation down the road that can easily supply this power? It's a discussion we hear quite often with electrification. Can the grid support it? Is the power available? And I'd say it's on a different level with a lot of the marine applications we're seeing than with automotive. Trying to get 14 megawatts of power in downtown Seattle for the Washington State Ferry electrification is a lot more difficult than trying to get a car charger in a garage, for example. Manual versus automatic. So the picture on the left showed a Davit that is more manual in its operation, and the other two photos show chargers that are automatic. So for ferries, that extra 2 minutes that an automatic charger will save is very important in reducing the charging power required. They have schedules that they need to make, and they need to stay on the schedule. For other applications such as tugboats, where they may go out and operate for a couple hours and then come back and charge for a couple hours, that automatic operation is not as important. So the higher cost and increased complexity of an automatic system isn't necessary for that application. Pure infrastructure. Where does the boat dock? Is there enough space on the dock to install these chargers? You can see that they all require some infrastructure. They need to be mounted. There needs to be electricity run to it. There's always more switching gear or conversion gear offshore, like transformers, switch gear, sometimes shoreside batteries that need to be installed. Does the space exist? If it does, very lucky. If it doesn't, then it's just increased cost and more planning and design work that needs to be completed. And one of my favorites, standardization. I think standardization of new technologies is key for a mass adoption. We are still in the everyone designs their own system, and nothing is really compatible across vessels or across vessel owners. And I think that will be moving into a time where there's more standardization of this technology, which will decrease the capital costs, which will make it more accessible for many of the operators. So it's a quick case study, and then I'll let Curt talk for a while. We have the E-Wolf, which is a Jones Act compliant all electric harbor tug that Crowley is building currently. It's under construction at Master Boat Builders in Alabama. It's expected to be delivered in Q1 of 2023. Looks quite nice without the exhaust stacks. So very quickly, there's 6.2 megawatt hours of batteries on board, which if you compare to the few hundred kilowatt hours that may be in a car, that may even be a lot. It's quite a high amount of energy storage, and the batteries take up a lot of space. The profile for this tug, specific to the Port of San Diego, really lent itself to all electric operation. So by all electric operation, I mean, there will be no generators running at all during operation. There are emergency generators on board to help in a case of emergency, but during typical operation, the boat will operate only from batteries. And in between runs, whenever it can, the boat will go back to the dock and it will charge. So this operation and this plot is from recorded data that was analyzed from previous year and a half, 2 years of standard diesel tug operation on the route. And you can see it's mainly focused at the lower end of the engine load. And the Port of San Diego is quite small. So this operation really lends itself to being all electric. The batteries aren't used very hard most of the time. It's quite a low rate of discharge. Next slide. So this is an example of the hold plan and an exploded rendering with outdated branding of the tug. And I think the key thing to realize from a design perspective is how different all the equipment is. There's a lot more cabinets involved and there's less moving parts. So rather than having a diesel engine with a shaft directly coupled to the L drive, it's all cables. There's a lot of cabinets. The batteries are cabinetized. The DC grid is cabinets. It's clean. So from a design perspective, it can be both easier and more difficult to place the equipment. You don't need to maintain a shaft line, but there's a lot of different form factors involved. And sometimes with tonnage considerations, it can get more difficult to place this equipment. it's been very interesting over the last few years, understanding the differences in general arrangements and how this equipment is placed. I worked on the Washington State Ferries, which has a 10 megawatt hour battery system, and the onboard DC grid for the cabinets with the inverters, converters, rectifiers, all that was huge. It was like a game of Tetris to figure out how to fit it in the boat. Excellent. And short charging. So the eWolf is planning to take advantage of short charging, obviously, because there are no engines on board. This is a artistic rendering of what the short charging station will look like. Crowley is developing an end-to-end shore power system from utility to vessel. There's going to be a vessel charge rate of 1 megawatt. Looking at the rates from the utility, there was a financial break point where we could only charge 500 kilowatts from the grid. Otherwise, it would get too expensive, and there would be no operational cost benefits to using this technology. So there was a decision to place containerized energy storage on shore. So those two containers contain a total of 3 megawatt hours of batteries. So about half of what's installed on the vessel. And this will be used to buffer the charging from the grid. So in a typical charge scenario, 500 kilowatts would come directly from the grid, and we would pay the utility rates for that. And the other 500 kilowatts would come from the energy storage on board or on shore. And in between vessel charges, the batteries would charge both from the utility and from the solar panel canopy on top. The system is also expandable. So as we get more electric tugs in operation, we'll be able to charge them from the same system. And I could probably talk for another hour on this subject, so I'm sure I skipped a lot of detail, but with that, I'll pass it to Curt.
All right, thanks a lot, Eileen. That was really interesting. So for the purposes of this next part of the presentation, we're really going to focus on the characteristics and design considerations for future fuels. And there's really 3 key points that we're going to cover in this section. Those 3 points are: what are the most common future fuels for maritime? And what are the vessel design considerations to accommodate these fuels? And then we'll close by talking about a case study for a hydrogen fuel tug that we've been working on. And you can actually see a rendering of that tug in the image here on this slide. And a couple of things to point out here. For the purposes of this presentation, we'll define future fuels as lower carbon alternatives to petroleum diesel. And although of the future fuels that we're going to be talking about, all but one, to my knowledge, are actually in use. But with respect to the term future, we'll consider that to mean widespread adoption in maritime. Okay, so what are the most viable future fuels for maritime? We're going to talk about 4 primary fuels, and this is not an exhaustive list. There are other fuels also being considered, but these are the 4 that are most commonly focused on now by vessel designers, vessel owners, and engine manufacturers and fuel cell manufacturers. So the 4 that we're going to talk about are methane, which is the primary constituent in natural gas. And we'll talk about methanol, hydrogen, and ammonia. And to really start to understand how these fuels differ from each other, we'll take a look at least provide an overview of their attributes. So we'll talk about the chemical composition and why that matters. We'll compare the lower heating values, so how much energy per unit mass there is. We'll talk about their densities and ultimately what that means for volumetric equivalency relative to diesel. And we'll also talk a little bit about boiling point and how that factors into the storage strategy. And then we'll also talk about what available energy conversion equipment exists to essentially convert the chemical energy in these fuels to usable electrical energy or mechanical energy for vessel propulsion. One thing to point out here before we change slides is that I've omitted biodiesel and renewable diesel, which are both really viable opportunities as lower carbon alternatives to petroleum-based diesel. But the reason I omitted them is that they actually don't have a significant effect on vessel design. There are a few design considerations that have to be thought through, but they're essentially drop-in replacements to petroleum diesel. And we've actually successfully used B20, which is a 20% biodiesel blend and 80% petroleum diesel blend in our fleet. And most recently used R99, which is 99% renewable diesel and 1% biodiesel. So just understand that those alternatives are out there, but they're excluded because they don't have a large impact on vessel design for the purposes of this presentation. Okay, so let's go through an overview of the various attributes of the fuels that we're talking about. And there's a lot of information on this slide, but there's a couple key takeaways that I want you to get from this slide and then the next slide. So first, let's do some comparison of the various alternatives. So if we start with natural gas, and we're looking at here this column here in the table, one of the things you'll notice is that the lower heating value is pretty close to diesel, but its density is about half. So what that means is that if you want essentially the same amount of energy as you would get out of a gallon of diesel, you need about 1.75 times the amount of natural gas in the form of LNG, which simply stands for liquefied natural gas. The other thing you'll notice is that the boiling point of natural gas is minus 161.5 degrees Celsius. That means it doesn't want to be a liquid at standard temperature and pressure. So if you want to carry it as a liquid, you have to cool it significantly and carry it as cryogenic fluid, which simply means that low temperatures are involved. Currently, there are commercially available energy conversion devices for natural gas, principally internal combustion engines, both two-stroke and four-stroke, spark ignition and compression ignition. Solid oxide fuel cells are also a possibility for energy conversion. With methanol, you'll notice that it's got about half the lower heating value compared to diesel, and the density is about the same. So when you go through the analysis, that tells you the volumetric equivalent to diesel is just a little over 2. One thing to really point out about methanol, and we'll talk about this in succeeding slides here, is that its boiling point is above ambient conditions. So it's the only fuel of the 4 that we're talking about that is a liquid at standard temperature and pressure. Similarly with ammonia, its heating value is about half that of diesel with a slightly lower density. So volumetric equivalency is about a little over 2, almost 3 in fact. And also notice the boiling point is minus 33.3 Celsius. So it's also would need to be stored as a cryogenic liquid if you were electing to store it as a liquid. And then with hydrogen, one of the things to really point out about hydrogen is that its lower heating value is almost 4 times that of diesel. It is really energy dense per unit mass. Conversely, its density is very, very low. So essentially what that means is if you wanted an equivalent amount of energy, you need a little over 4 times the volume of liquid hydrogen as you would for diesel. It's also interesting to point out that its boiling point is the lowest of any alternatives that we're talking about here at minus 252.9 degrees Celsius. And with fuel cells, or sorry, with hydrogen and liquid ammonia and methanol, fuel cells are options for energy conversion, as are internal combustion engines. And also want to point out, there are a couple companies in the industry right now focused on reformer technology with methanol, which simply means splitting the hydrogen from the carbon and oxygen. And then you essentially end up with pure hydrogen that can be used in a proton exchange membrane fuel cell. Similarly with ammonia, there's a company out right now that's a startup focused on an ammonia cracking reformer. So splitting the hydrogen from the nitrogen and then converting energy in the form of, or using a proton exchange membrane fuel cell. So it's a really exciting time to be in the industry. A lot's changing very, very quickly. So before we move on, I just want to quickly touch on chemical composition. And the key thing I want you to take away here is that Two of the fuels that we're talking about have carbon in their molecular structures and two do not. So what that simply means is that when considering tank to wake emissions, so just the vessel and what comes out the stack, the fuels with carbon in their molecular structure will actually produce carbon emissions, and those that don't have carbon will not. So when you look at methane, it's got 1 carbon and 4 hydrogens. And similarly, methanol has 3 hydrogens with 1 carbon and then an oxygen and then another hydrogen. So these two fuels will actually produce carbon emissions tank to wake. If you look at ammonia, it's 1 nitrogen and 3 hydrogens. So it will actually not have carbon emissions tank to wake. And then similarly with hydrogen, it's just H2, so 2 hydrogens, so no carbon emissions when converting the energy from hydrogen into electrical or mechanical. Okay, this graph, I think, provides a nice overview of what we just talked about with respect to energy density per unit mass, or in this case, the lower heating value, and also energy density per unit volume. So again, the key takeaway from this is that when you're designing around these future fuels, be aware that if you're trying to get an equivalent amount of energy as you would with diesel, you're going to have to accommodate a greater volume. So just like we talked about, liquid natural gas is about 1.75, jumping all the way to liquid hydrogen, it's a little over 4. Interestingly, we've also included compressed natural gas, which is also a little over 4. And then when you get to compressed hydrogen, in this case, in the pressures we're looking at, which is 207 bar or 3,000 psi G rather, is almost 18 times the amount of volume. Contrast that with this blue line, which is energy density per unit mass or lower heating value, and you can see that there's perhaps a bit of a paradox on the surface that liquid hydrogen or compressed hydrogen in general has a very high energy density per unit mass, but again, because of the density of hydrogen, it requires quite a bit greater volume to get the same energy per unit volume as diesel. Okay, so now we're going to jump to design considerations. And there are actually a tremendous amount of design considerations that you have to factor in when designing around these future fuels. But I want to talk about 3 of what I consider to be the most important. So we'll start with the regulatory compliance. And the important thing to understand here is that the pace of innovation and vessel design exceeds that of what the regulators can develop in the formal documentation and guidance. So why that's important is that in most cases, I think the only exception would probably be natural gas, which is well understood now, at least in the regulatory framework, is that when you're embarking on a design project, you need to include stakeholder engagement with the regulatory bodies early and often. So what you want to think about, as this slide indicates, is who are your primary stakeholders. Considerations are class, so ABS, DNV, et cetera, the flag state, and then the International Maritime Organization. And a really good place to start when you're embarking on this regulatory framework is to defer to the IGF code and IGC code. And the IGF code is the International Code of Safety for Ships using gases or other low flash point fuels. So the 4 fuels that we're talking about here are all low flash point, which is less than 60 degrees Celsius. Or if you're designing a vessel that's carrying these fuels as cargo, you would look to the IGC code, which is the international code for the construction and equipment of ships carrying liquefied gases in bulk. It's also very helpful to defer to some of the existing guidance documents that are out there. We've listed some here on this slide. And if you take the case of a vessel design that's going to be in the US, so the Coast Guard will be the flag state, then what you do is essentially embark on a design basis agreement, which is simply a formal document that describes the regulatory framework that you're intending to use. And at the end of the day, what you're really trying to do is prove equivalency and safety compared to the existing regulations. So it's a bit of a complicated subject, but just from this slide, take away that if you're embarking on a vessel design project, regulatory compliance and stakeholder engagement is a key factor. I want to talk a little bit about the regulatory maturity. This is kind of an important point because it's not the same for the four future fuels that we're talking about. So if we kind of go from least mature to most mature, we could consider, although it would be up for discussion certainly, that ammonia is probably the least mature. And if you think a little bit about what might be sort of in that intermediate range, hydrogen and methanol would fall into that category. Although there are examples of vessels currently that use hydrogen as a fuel and methanol. I believe it's the Santa Germanica that's actually using methanol as a fuel. And then if we focus domestically, the Sea Change is the first hydrogen-fueled vessel to be built and operated in the US. So there are examples of vessels that use hydrogen and methanol as fuel. And of course, everyone's probably aware of Maersk's commitment to using methanol in their new build container ships that are ordered. And then in terms of most mature, that would be natural gas. There are many examples of vessels using dual fuel LNG for their energy source. And to the right, you can see a picture of the El Coqui, which is one of our 2 LNG dual fueled Conroe vessels in operation. And just above that is an outboard profile rendering of the Hyzit, which is again the hydrogen tug that we'll talk about here as part of the case study. Okay, so the second major design consideration that we're going to talk about is fuel storage arrangements. And recall from our discussion around the attributes of these future fuels is that all but methanol need to be stored cryogenically if you want them in the liquid phase. So we'll talk a little bit more about that in the next slide. But on this slide, let's just talk a little bit about what are some tank types that you might consider for vessel design. The first is traditional hull tanks, which are really designed for atmospheric pressure. They're integral to the vessel hull. Also think of as structural tanks, and really allow you to get the highest amount of volumetric efficiency in terms of fuel storage and the available space in your hull. A second type would be type A. This is actually an independent tank, so not structural, although prismatic. So it's making a pretty efficient use of the available space. This tank would be suitable for cryogenic fuels or cargo. However, given its geometric configuration, it's not suitable for higher pressures. And talking about the details of that is a little bit beyond the scope of this presentation, but certainly if you have any questions about that, feel free to reach out and we can talk in more detail. Another example, and perhaps most common, is a type C tank. You can see those phantomed in green. Our Conroes that we looked at in just the previous slide have 3 type C tanks. These are pressure tanks capable of containing higher pressures and suitable and very common for cryogenic fuels and cargo. The downside is that the volumetric efficiency is quite low in terms of the usable space for fuel or cargo relative to the hull volume. Also important to point out, although we've illustrated here cylindrical shapes, it's also possible to get multi-lobe, so bilobe and trilobe, which can actually increase your volumetric efficiency. Let's see, try to be conscious of time here. I think I'll speed up a little bit so we can get to the case study and allow some time for questions. But with respect to design considerations, getting back to this whole concept of cryogenic fluids or fuels rather, and why that's important for tank loading is that when you're talking about cryogenic fuels, whether consumed for propulsion or energy or cargo, you actually not only lose some volumetric efficiency in terms of having to use independent tanks, but there's also a consideration that your loading, so how much fuel you can put in that tank, is limited. And it's limited because cryogenic fuels, as they absorb heat energy, the density actually decreases. So for the same mass of fuel as it takes on heat, the required volume increases. And you have to account for that when you're sizing your tanks. And specifically, the deduction occurs when you're looking at the relative density of the fuel or cargo when it's loaded, and the relative density of the fuel or cargo at the relief valve pressure setting of the tank. So essentially what that means in a couple of specific examples, when we're looking at liquefied hydrogen, you might see that the usable volume is reduced by up to 30%. And in the case of LNG, it could be reduced by up to 20%. So that's really key in understanding how much volume you might need if you're designing a vessel around one of these future fuels. Additionally, although factored into the volume reduction figures we just talked about, for cryogenic fuels, it's necessary to retain a certain amount of heel. And that is because you want to keep the tank cool even when the volume of cargo or fuel is low. Cooling down the tanks is a really expensive and time-consuming process. So, and it should happen rarely in normal operations. So having a little bit of heel allows you to keep the tank cool. You can actually recirculate it through spray rails in the tanks and also manage the tank pressure. Also want to talk quickly about methanol. We mentioned earlier that methanol is the only of the four options that is a liquid at standard temperature and pressure. So that is one important consideration, is that you can essentially put methanol in the integral tanks, like we looked at in the last slide, although it is a low flashpoint fuel. So current design guidance and regulation focuses on a requirement for cofferdams. So there is also a limitation on usable volume for methanol, even though it is a liquid at standard temperature and pressure. Okay, so the last of the three major considerations that I want to talk about are hazardous zones. And I can't stress this enough, but when you're starting a new design or even a modification, say, or a retrofit of a vessel using one of these fuels, that you need to start the evaluation and arrangement of your hazardous zones at the same time as you're starting your arrangement. And that is because the regulations right now, even if you're putting together a design basis using a framework, are pretty prescriptive in that any source of emissions of these fuels, because they're low flash point, requires an offset from gas safe spaces or non-intrinsically safe equipment or electrical equipment that is not rated for the appropriate hazardous zone. It's a big topic, not one that we can go into a lot of detail in this presentation, but you can see in the figure on the bottom here, this is a snapshot of our LNG bunker barge that's currently under construction. And the cross-hatching is actually defining the boundaries of the hazardous zones. It's not so much of a challenge on larger vessels, but it's a significant challenge on smaller vessels because the requirements are prescriptive. So in general, hazardous zones are classified into three categories. There's zones 0, 1, and 2. Zone 0 is when an explosive gas atmosphere is always present. Zone 1 is present in normal operation, and Zone 2 is not normally present, but possible. So things like tank vents, which you can see here in the snapshot, the largest zone is actually attributed to the vent for the LNG cargo tanks. And in the image on the right, you can see the sea change, which we mentioned a few slides ago as the first hydrogen-fueled vessel in the US. And you can see this really big mast on the stern. And what that is the vent that's connected to the hydrogen tanks. So you can see the impact that has on the design, and I think it helps to illustrate the importance of hazardous zones. Maybe one thing to mention too before I move on is that although the hazardous zone definitions and boundaries are prescriptive, they're not necessarily directly applicable to the type of fuel. So one way to potentially reduce the boundary requirements of hazardous zones is to do what's called the gas dispersion analysis. And that essentially looks at the concentration, the flammable concentration of the fuel, should there be a release in various environmental conditions. Okay, just want to talk about a couple other key factors. We don't have time to go into these in detail, but they are important to think about. So bunkering strategy, how are you going to refuel the vessel? The image on the right is actually our Conroes again getting bunkered. They bunker from land-based tanks in the port of Jacksonville. You also need to think about emissions requirements. So regulatory, customer requirements, also corporate ESG goals, which are environmental, social, and governance. So Eileen was mentioning Crowley is committed to net zero across all scopes by 2050. That is an ESG goal and helps drive our thinking moving forward. Also, you need to think about the technological readiness of energy conversion equipment, firefighting, fuel supply. So thinking about what's the production, how does that align with your emissions goals, both regulatory, like we said, customer and corporate. What pressures will there be on the supply chain of the fuel that you choose from other industries? And then, of course, cost. All these projects that we're seeing cost more than conventional designs. And that may not always be true, but it's certainly true now. So that is a significant factor in evaluating the viability of any project. So when we're talking about cost, you can think of it as capital, operational, and then that rolls up into total cost of ownership. Okay, I know we're running short on time, so I'll cover the main points here for the case study. What I wanted to talk about was the hydrogen fuel tug project that we've been working on. It's called the HYZET. It stands for Hydrogen Zero Emission Tugboat. And it's developed by a consortium of industry-leading organizations. You can see our logos there on the slide. And really the focus of this project is to assess the feasibility of megawatt-scale hydrogen fuel cell harbor craft. And what that looked like for this particular design is a tugboat. So the desired outcome from this project is really an actionable design. So what that means is a design that has been vetted both from a technical and also regulatory standpoint, so that if the funding is pulled together and hydrogen supply is determined, then the project could move forward into actual construction and operation. Also as a test project to accelerate the decarbonization of the marine sector, and importantly, to create hydrogen demand. Okay, so just real quickly, some of the particulars on the tug. That's about 100 feet long, the 47 feet beam overall. In terms of installed power and energy storage, the primary power source is hydrogen as fuel at around 3,500 kilograms stored as liquid. The fuel cells cumulatively are 2.4 megawatts. And then we have about 1.74 megawatt hours of batteries installed, so energy in the form of batteries. And this is a 90-ton ship assistant escort tug. So we have over 5 megawatts of installed propulsion power in the form of L drives. So if we look to the right here, we can see the operational profile. And as Eileen talked about, tugs are really good test cases for these hybrid type propulsion systems. And that has a lot to do with load variability. So you can see here that most of the time, this tug, which is going to operate out of the Port of LA, spends at loads less than 50% of MCR. In fact, for the Port of LA, which is much bigger than the Port of San Diego, the transit times are longer, and thus the amount of time that the tug actually spends at anywhere near full power is very, very small. Okay, so this is an inboard profile. Just to highlight a couple things here. One of the prominent features is this vent mast. And again, similarly to the sea change, the ferry that we looked at a few slides ago, That is to get any potential release of hydrogen from the tanks far away from the vessel. Maybe one other thing to mention too, to Eileen's point earlier, when you look at these vessel designs from the outside, they actually don't look that much different from a conventional tug design, but once you start looking inside the compartments, it's very, very different. So let me quickly jump to the main deck plan. One of the things you'll notice here is that we have a fuel cell room that is actually not adjacent to any accommodation spaces. So it's separated by a passageway. So the fuel cell room will be gas safe in normal operation, although you have to consider the fact that there may be a leak or unintentional release of hydrogen. So that room is currently separate, or rather not adjacent to any accommodation space. Now, if we go into the upper hold plan, you'll notice where the engines typically are, we have two liquid hydrogen tanks. And an important thing to note here is that these tanks are surrounded by a bulkhead. There are no entrances to this from the hold. And that is because this liquid hydrogen tank space is hazardous in normal operation. So immediately forward to that, we have the switchboard room with the drive cabinets. Eileen spoke to that in detail about how the incorporation of batteries and electric power drives you to have to also accommodate drive cabinets and switchboards. And then if we go to the next level, we can see the battery room, which is where our battery racks will be. So I think that is it. Thank you very much for the opportunity. And it looks like we just have a couple minutes for questions, but it's not a lot of time to answer them. So if anyone has any questions that we don't get to, please feel free to reach out to us. We'd be happy to speak further.
Okay, well, thank you very much. Are there any questions? Yes, David.
Thanks so much for laying the fact. Eileen, you mentioned that you couldn't have this 1 megawatt charge on the tugboat, and therefore you needed the containers. Like, could you elaborate a little bit why that is? Just the peak demand that they couldn't handle, or?
I'm sorry, Bradley, we couldn't hear that very well. Would you mind repeating the question? I guess, Bradley, if you could repeat the question, we can hear you really well. So.
Yeah, the question was earlier in your presentation, you mentioned that there was a 1 megawatt limit due to whether it was containers or otherwise. Could you elaborate on that?
Yeah, so the 1 megawatt limit on charging of the eWolf was actually a design choice. So charging rates can be limited depending on a few different factors. One of them is the size of the batteries. So for the batteries that are on the eWolf, looking only at that aspect, they could handle 12 to 18 megawatt charge, which is obviously quite a bit larger than 1 megawatt. It can be limited by the selection of the drive or conversion equipment on the vessel. In this case, it's limited based on a Crowley design choice of the actual charging infrastructure. So the actual plug is limited to 1 megawatt. And this decision was made looking at the operational profile and taking a realistic look at what power is required to charge the vessel so it can still maintain its operation and flexibility. So we are seeing a lot of other instances, more so with ferries, where they have to charge that fast. So 14 megawatts, I think there's some talk of 30 megawatt charging up in Canada, which is quite significant.
Vicky first, and then the Dean.
So I got a quick question for this last case study that you looked at, the hydrogen tug. The consortium you put together included DNV, and I was wondering if there was any benefit for using them over, say, like an ABS, or do they have more experience in this, or how did you come to that conclusion to bring them on to the team as opposed to someone else?
Okay, I think I caught most of that. So the question is why did we pick DNV specifically? over another classification society for the HISET consortium. And the answer is, I'm not sure actually how the consortium actually came together. It's been, I'd say, over a year. But to be honest, I think, ABS would be fine too. I think the important thing is that there is representation from a classification society to help go through the risk assessment, actually, which we just conducted about a week and a half ago as part of that project. So yeah, I would say certainly have a lot of respect for DMB, but also have a lot of respect for ABS as well. So I would say, either would be great partners for the project.
Okay, thank you.
Matt?
In working on the E-Wolf, what battery discharge level were you assuming for normal operation? Meaning, how far can you take those batteries down before you really have to recharge them? Number one. And number two, are you seeing any movement in this area that you can actually discharge batteries to a lower level than previously been able to do?
So
Yeah.
I think I caught the first one, but I didn't get the second question. You wouldn't mind repeating?
Sorry, I missed both ends of that. Sorry, Matt, just.
Was it depth of discharge, the first part?
Yeah, so the first question is, what's the depth of discharge you're assuming for normal operations of the E-Wolf? And then the second part of that question is, looking at what you've come across in your design work, do you see the ability to discharge deeper coming in the future, or is there a baseline limit we're dealing with now?
So the first one, the vessel was designed with the battery size to accommodate essentially two harbor operations. So I think as it's the first Crowley vessel that is all electric, and the first tug in the US, I think it was designed probably a bit conservatively. So I think in normal operation, we'll probably see that we're not using the full available depth of discharge range. And then with batteries, it is not a straightforward equation for aging and what you can assume as the standard available energy or available depth of discharge. I think a good baseline is to assume the end of life energy capacity is 70% of the standard. So with the E-Wolf 6.2 megawatt hours at the end of life, there will only be 70% of that energy available for use. And even within that, there's going to be limits on the voltage range. So you can't charge the battery up to 100% because you'll hit voltage limits. Because to charge the battery, you have to charge at a higher voltage than the rest voltage. And it's the same with discharge. When you're discharging the battery, there's an immediate voltage drop with the electrochemistry. And the harder you use the battery, the higher that voltage drop. So if you're using the battery at a higher C rate or at a higher discharge, you'll be able to use less of the available energy than you would at a much lower discharge rate. So it's really application dependent. And I would really urge everyone that's considering designing an electric vessel to have some pretty in-depth conversations with the battery manufacturers and the experts in there to really understand how the batteries are being used and what is considered in the aging calculations.
Great, thank you very much.